This video has been supported by PCBWay. Hey guys, here's a special Christmas story that I somehow never got around to telling properly. Santa's helper, equipped with reindeer horns and all, delivered the single greatest Christmas package of all time. Oh, and maybe also took the single greatest risk by putting it in front of the door without having my signature. But all went well, as you may know. It's been in all the videos. This is the Rode & Schwarz MXO4 series oscilloscope front cover. In this video I'm going to show what I, a clueless DC person, has learned while test driving this absolutely exorbitantly overkill tool, and what valuable capabilities we can unlock on every scope using open source hardware probes from PCBWay. When it had only just been released, unleashed on the market, MXO4 got a lot of publicity. It made waves with its revolutionary 12-bit ADC. Now, I'm a bit of a bit enjoyer myself, but that's kind of what these are for. I've never felt the need for more vertical resolution in my oscilloscopes. But let's see if this beauty can convince us of its value. First of all, I had to convince Rode & Schwarz to give me firmware updates. Just like Keysight and many others, they are making it perfectly clear that they have no interest in dealing with individual consumers. And here's an unpopular opinion. I get it. No longer dealing directly with problematic, entitled, and legally protected end users, who spend no more than pocket change in the grand scheme of things. Must have economic advantages, sufficiently large, I'm sure the suits will have determined, to counteract the small blemishes in these companies' reputations. But did they also foresee the grumbling of an inconvenienced YouTuber? I get it, but I don't like it. I have a business since 2018, but not even that was enough to get an account approved for access to Rode & Schwarz Plus premium content, like the user manual and firmware updates. You registered with an open source email address. What the hell is an open source email address? Like Gmail, Hotmail, QQ, or another public email client. Did I? Anyway, there's end of sentence punctuation missing. Due to security standards, it is not possible to verify your affiliation with the company you register as your employer. I have not in fact registered this company as my employer. This is my company and my company's exclusive email domain, if you don't mind. You get the idea. Not a good experience, but sadly normal nowadays. For the intended clientele of larger company employees, this will go perfectly smoothly, I have no doubt. Technically, the firmware updates are well worth fighting for. They were published frequently and still are over 2 years after the launch, often with very valuable improvements. For example, this graphical zone trigger is relatively new, and it's powerful for catching rare anomalies, without even having to describe them in terms of sequence, edge, glitch, width, front, window, hold off. XY mode, the most culturally impactful oscilloscope feature ever, has only just been patched in January 25. So development is ongoing, and that is wonderful to see. I'm not sure actually if there are any practical real-world applications for XY mode nowadays. Please leave a comment if you've used this for anything serious in the last decade or so. I love having it available no matter what. At a very first glance I was wowed by the display size, and slightly worried about its enthusiastic reflectivity. To my great relief, that is only a protective film for what is actually a very tastefully deglared, microstructured, real glass touch panel. Bye bye. So no worries about leaving greasy fingerprints. This could be cleaned with aggressive solvents without a problem. Excellent stuff, but I will continue to wear gloves. It's a trademark at this point. The display is not just inflated for good looks, it also has a delicious Full HD resolution, which is mirrored in all exported screenshots. And certain multi-window arrangements are possible, so we can put all of this real estate to good use. EEVBlock had the balls to do a thorough teardown on one of these. I don't think I could add anything of value to that. So I will abort this mission shortly, but 2 of my personal highlights are right here in the back. First, there is a high-quality gaming-grade cooling fan, making this RGB battle station silent under normal load and nearly imperceptible under stress. Second, I haven't verified this yet, but it is my impression that the whole scope runs on a single 12-volt power supply, from which it derives all the other rails it needs itself internally. If true, it'd be perfectly trivial to feed it battery power for mobility, floating measurements, and common mode leakage analyses. Although the last point, where we use the scope's 1 megaohm input impedance to ground as a current shunt to determine what flows into or out of other devices, that works fine just with its normal switching power supply. It itself must have good common mode isolation. It's a more common feature nowadays, but a couple of years ago Rode and Schwarz's RTB series was one of the pioneers, certainly the first in my lab, to offer a high-resolution, high FPS live stream of whatever is on the display, plus a replica of the mechanical user interface. So valuable for everybody whose job involves presenting, documenting, teaching, YouTubing, or even just commuting between two desks. Of course, MXO4 offers some improvements over this, such as a file explorer and a sexy after-dark mode. I wonder if one could monetize this, like sell interactive MXO4 online live sessions by the minute for test gear lovers, soon on onlyppms.com. My comfort zone, or should I say band, my comfort band is between DC and 10 Hz, but that doesn't mean that I'm not excited about some good RF tools. A good example would be the category of dynamic signal analyzers, popular usually in acoustics and metrology. It's a lower noise front end feeding a higher resolution ADC than what we usually see in oscilloscopes and spectrum analyzers. And then there's just a computer on top calculating an FFT spectrum based on memorized samples. Sounds strangely familiar, doesn't it? The purpose is to plot noise density spectra for components or circuits. Wouldn't it be great if such an expensive, bulky machine would just be built into many modern oscilloscopes? Let's see if Rode and Schwarz made it fit. By shorting out a channel, limiting its bandwidth to the absolute minimum, and by activating HD mode, which can further trade bandwidth for lower noise, averaging multiple ADC conversions into one point. In those settings, MXO4 gives us a trace with so little noise that it's only 2 pixels thin, even though we are in the lowest voltage range already. I'm seeing a spectacular tens of microvolt overall noise floor after choosing 1 kHz bandwidth. For, say, an HP 3562A dynamic signal analyzer, the spec is less than minus 126 decibel volt, which corresponds to less than 500 nanovolt, when using less unhinged units. Our modern contender is in the same neighborhood with the aforementioned settings. Amazing for an oscilloscope, and easily one-uppable with an additional preamp. To get a good read on those really low frequencies, like millihertz, we have to collect samples over a very long time, kiloseconds. And to see high frequency content, we need a high sample rate. Maintaining a high sample rate over a very long time is always difficult. Like this scope can generate so much data so quickly that it becomes a real problem to get it out of there, for processing on another machine, for example. Who wants to handle multi-gigabyte CSV files? So it's good that MXO4 has a huge sample memory of 400 million points per channel by default, or 800 million points as a costly software option. The standard memory is already excessively large for all I ever wanted to do, and it comfortably allows to capture enough information to see millihertz to kilohertz in one go. And I think that's all the hardware requirements of a dynamic signal analyzer satisfied. Processing power? Come on. If it was possible in the 80s, then this modern touchscreen monstrosity will be able to do it effortlessly, pretty sure. Well, it works, of course. I would use the flat top 2 window type, and then with resolution bandwidth I can choose how detailed of an analysis I want. In exchange for finer resolution, it needs to be fed more samples. I can freely choose what frequencies I'm interested in, for example 0.1 to 10 Hz. It's the most common band for DC-focused datasheets, like voltage references and auto-zero amplifiers. This is nice. The built-in spectrum analyzer would probably also accept insane inputs like DC to microhertz, and then ingest days worth of data to try and make that happen. I only have one little problem. When choosing a logarithmic scale for the x-axis, no starting points below 1 Hz are accepted. I understand that it can't be 0 Hz, and I understand that such esoteric niche use cases aren't necessarily the prime design goals of a futuristic gigahertz instrument. But if I could go down to maybe 1 millihertz here in a future firmware update, that would be just perfect. That's kind of where the most interesting stuff happens. Doesn't matter if it takes forever to capture the data. The full 1.5 gig bandwidth that is proudly proclaimed in the top right corner seems to be only available through an interlacing technology. So only on channels 1 or 3 with another inoperable channel slaved to them. And only with 50 ohm termination, then it works great. .5 gig is also not a hard limit exactly. It might be the -3 decibel point of the front end only. Here's 2 GHz coming up, and it's shrinking but visible. With 5 gigasamples per second, we could theoretically still see 2.5 GHz frequencies. But the front end is quitting just as we get there. Good enough for a beginner. In terms of normal spectrum analysis, MXO4 is very good too. We can ask it to perform min-max hold and average arithmetic on spectra. These graphical zone triggers can be applied in frequency domain windows too. I was tempted to say that that was unique because I've never seen it before anywhere. But I don't get to play with that many luxury scopes on a regular basis, so not entirely sure. In combination with the crazy sensitivity, it's fantastic for sniffing out EMI problems. Naturally, on my own carefully laid out boards, like this one, I never find any. It'll automatically label peaks if we want that, and it's wicked fast too. The advertising materials keep talking about over 45,000 FFTs per second. Sounds nice, but I feel like that in itself is not a very valuable specification. Like, I would prefer to know what percentage of time can be ingested and evaluated by the FFT, and how much blind time there is between captures. So-called real-time spectrum analyzers are another prestigious subset in the FFT analyzer category, and what they can do is see 100% of the time. Not even the shortest, rarest bursts can escape their watchful eyes. Could they escape MXO4? Well, these statistics seem to be for the time domain stuff, the normal oscilloscope trace in the upper window. 85% of time captured would be pretty good, but the spectrum analyzer sees only that narrow window, between vertical cursors at the center of the screen. If we demand a higher FFT resolution, the window gets wider. But then there is exponentially more processing to do, causing blind time where no acquisitions happen. This matters only for rare, short events with no other means of triggering. In those cases, it can be a bit tricky to figure out the optimal parameters for minimal blind time. But I'm very happy to report that with some concessions in the resolution bandwidth, the spectrum analyzer span, and by disabling all optional processing time consumers, such as automatic markers, our candidate can in fact achieve a self-reported 100% of time captured. That gives it high probabilities of interception, which is amazing, but not quite enough to earn the prestigious title of real RTSA. Because imagine if a single unfortunate wave of interest arrives just in time to be sliced in half between 2 captures. Neither FFT would recognize it for what it was. That's why real, specialized RTSAs have to run simultaneous overlapping captures and conversions, to guarantee that nothing is ever lost in this way. Overall, MXO4's spectrum analyzer is very good. Better than what I would have expected for something that's just thrown in together with an oscilloscope. For completely blowing my mind and earning a better grade than very good, it would have needed a little bit more, a waterfall display or a software-defined radio app. Or one of the built-in generators to be able to be turned into a tracking generator for reflection measurements. On a closely related note, this isn't the most important spec for my personal area of interest, but Rode and Schwarz are rightfully proud of their waveform updates per second specification for this model, outpacing even much higher-end scopes, if not all of the competition, with over 4.5 million waveforms per second under some conditions. What's that good for? I couldn't even view all of those waveforms on an overclocked gaming monitor. Well, a waveform update includes, of course, evaluation by the trigger system, min-max hold, measurements or an app, to make something visible. To be fair, it is easy to bog down the ASIC with additional tasks or unsuitable acquisition settings. I believe it hasn't caught a single one of the short LoRa transmissions that I've been sending out into the ether once per second in this scene. Even with less than optimal settings, it is amazingly fast. But that was just a mocking imitation of other scopes. Here's what we are really capable of. Not only triggering on every transmission, but millions of times per second. LoRa uses these spread spectrum chirps to talk. This isn't a low-quality transmitter wobbling around. Let me rephrase that. That is a low-quality transmitter wobbling around, but that is actually its working principle. And while we don't have a waterfall display available just yet, there is an automatically maintained history that we can rummage through or play back. I wonder where they store this. This seems like a crazy memory-hungry facility, but nice to have. Now that I've mentioned the app keyword a few times, I guess we can avoid it no longer. The app drawer or home button for it. It seems underutilized at the moment. I only come here to launch XY mode or the frequency response analysis tool. So I would like to formally request an app store and some games maybe. I'm sure the suits would approve if they could also sell software options there. Spectrum Analyzer is included by default in all trim levels. Arbitrary waveform generator, frequency response analysis tool, and numerous digital decoders cost extra. Should we do a cheeky little frequency response analysis on an old Capco bipolar operational power supply? What a mouthful. This is basically a mains-powered operational amplifier, with a feedback resistor built in for gain setting. The scope will generate and monitor excitation waveforms on the input, and compare that to what it sees on another channel. This way we can let it analyze gain and phase response of individual components, subcircuits or whole devices over a wide frequency range and present the results as a nicely formatted Bode Plot. Did you know it was Bode Plot? I was completely sure about it being Bode Plot all my life. That does not bode well. Sweeps with the internal generators can be configured between 10 MHz and 100 MHz. Love that it goes down to millihertz here for DC-focused filters. In this setting, while monitoring its electrical output, we are testing the amplifier only. Theoretically, once we know that baseline, we could also hook up a measurement microphone and benchmark the speaker, if there's anything left of it. And once we have such a well-characterized audio source, we could start testing microphones. But that is not the rabbit hole for me, I'm afraid. I have no doubt that this affordable, high-quality speaker fulfills its datasheet power rating. Do you? Yep, pretty cool. Both the FRA software and Capco's performance. I will say that in the past it took me no more than 20 minutes to set up a crude replica of this in Python. It's basically just setting some arbitrary waveform generator points, while reading back some RMS measurements. Bro, listen, do you have any idea what this is? I'll tell you anyway. It's a thermocouple temperature sensor. 2 different metal wires spot welded together. Normally it takes a special preamplifier to read these. Not anymore. Straight into an oscilloscope channel it goes. I can't stress enough how impressive this 18-bit HD mode is. It doesn't truly give you 18 noise-free bits in the lowest voltage range, when trading in the bandwidth all the way down to 1 kHz. The effective number of bits is something like 10 here, resulting in reliable couple of microvolt readings. That is absolutely wild to me. I don't have much to say about the normal oscilloscope stuff. It's all there. I felt right at home immediately after years of Tektronix. The measurements menus are sorted alphabetically, I think, so when just looking for peak-to-peak and RMS, one has to do a little bit of scrolling. No problem really, this is all excellent. The user interface is also snappy under all conditions, and the whole scope has been 100% reliable. No time-wasting bugs or hidden features that have to be researched. Wanna see a little goodie that ties together two incredibly unlikely, seemingly incompatible subjects? Here's how to do ultra-low current calibrations for electrometers and such, using only an arbitrary waveform generator and a low leakage capacitor. The can of beans here is an air capacitor, made from interlacing INVAR plates. 1000 picofarad acting as a differentiator. When feeding a ramp voltage waveform into one end, its other terminal will put out a current waveform proportional to the rate of change. So a beautifully calculable DC, dependent mostly on accurate timing and therefore much more accessible than obscure, noisy, high-value resistors. We'll try to use this for real in another video soon, TM. The included standard issue passive probes are fine. They are good quality, made in Germany, fixed for the 1 megaohm input termination. On one hand, I like that they are long and thin. On the other hand, do we really need another neck diameter standard? This is a Tektronix ground spring, and it fits neither Keysight nor Rohde & Schwarz passive probes. No wonder I can never find one when I need it. The optional logic analyzer probes are excellent. They have an active buffer near the business ends to represent a high impedance to the signals of interest and to translate them into a long shielded differential cable for maximum EMI immunity in spite of long length. Pretty much all scope probes from every high-end manufacturer nowadays, certainly all active types, are ear-tagged with an identification EEPROM and some unique interface next to the BNC connector. That way, their calibration and compensation coefficients can be memorized and applied automatically. Customers can effectively be locked into manufacturers' proprietary ecosystems, and active probes can be powered straight through the scope. No need to mess around with external support boxes anymore. For, I'm sure, our own safety. For, like, protection from unlicensed aftermarket probes and software option piracy. The logic channels on here will not turn on without the original probe plugged in. So, clearly, the test and measurement equipment giants only have our best interests in mind. Sadly, there are some ungrateful individuals out there who don't seem to enjoy their golden cages. Or they are just poor and can't afford a few $5,000 active probes. To me, it is a mystery why anybody would even consider using open source hardware oscilloscopes. So I thought I'd try a couple and see how bad and unreliable they really are. These exact near-field probes might not be open source hardware, or they might be, but I paid a single-digit number of money for them on AliExpress. They are so simple that I'm sure some open designs are published somewhere. The loops are H-field probes, which are primarily sensitive to alternating magnetic fields. The pointy ones are E-field probes, and they are for sensing alternating electric fields. The most common use case for these is to test a newly designed product for radiated emissions, before handing it to an ultra-expensive EMC compliance testing laboratory for certification. Rather than being a little stickler for rules and compliance, these probes can also be used for the exact opposite, for non-invasive side-channel attacks. When trying to do something unusual with a locked-down embedded system, it is often helpful to look for clues in its secondary signs of life. Patterns in power consumption or radiated emissions could reveal after what time a password check fails, how many characters we guessed right, when a certain peripheral is accessed, or when the most promising glitch injection times are. MXO4 is a great partner in crime because it can see almost everything without even needing a preamp. These are also not exactly open source hardware probes yet. I just modeled them up one afternoon to try. Should be really easy to recreate if it works. These are bobbins for forming 3 coils, one outer send coil and 2 inner receive coils. If we arrange 2 or more equal receive coils right next to each other, and then insert them into a send coil, then we have built a basic eddy current probe for non-destructive material testing. Professional versions of which can cost many thousands of monies. The idea is to drive the send coil with a waveform generator, be it built into an oscilloscope or not. Then, if you want to, say, buy this expensive cyber car, with its lovely new duct tape paint job, Or if you have to inspect a mission-critical metal part or weld for voids or cracks, then you just have to look at the difference between the receive coil's outputs. When probing uniform metals, they should be under the same influence of induced eddy currents. When approaching a boundary where the eddy currents need to take a detour, then there should be a measurable difference between the receive coils, pointing towards a hidden flaw in the material. Certain experiences in my early days of tinkering with oscilloscopes have conditioned me and given me these loud mental alarm bells that go off whenever I approach a mains circuit with a scope probe. In theory, as an emergency workaround, it's possible to use some attenuation and high impedance input termination on 2 channels with a math difference operation to get something out of this without casualties. But in general, no thanks. That's what differential probes are for. And I would probably call these the most universally useful must-have scope accessories. I've had this Hewlett-Packard 1141 set for an eternity. It's good because it has these interchangeable attenuator tips for higher voltages. And the main handpiece is based on some ceramic hybrid modules and resistor networks. Because of that, it has good flatness from DC to 200 MHz. But it's a bit inconvenient with that large, separate support and power supply box. And when considering modern, high-speed digital differential signals, 200 MHz actually don't get you very far anymore. With that, we might still be able to make out the rough outlines of USB 2.0. Barely. Luckily, we just got a few more packages. And if the luck continues, there's going to be a modern, open-source hardware, multi-gigahertz active differential probe in there somewhere. Our sponsor, PCBWay, who has etched, laminated, plated, screen printed, sliced and diced all of these beauties in a matter of days, would have been very happy to help us out with some of their high-tech, high-performance substrates. For example, 2 flavors of Rogers ceramic fiber laminates, with improved dielectric losses, leakage currents and thermal stability, are even available in their standard production line and therefore affordable. Under advanced PCB, some higher glass transition temperature materials are offered, and even PTFE-based gigahertz substrates are available to order. I think I will have a good excuse to make my friends at PCBWay reach for their upper shelf good stuff soon. But not this time. These open-source hardware active voltage probes by Andrew Sonnenberg seem to rely on miniaturization and the signal path hardly ever touching the PCB outside of components. That makes assembly a little bit tricky, but there should be very low board parasitics automatically. That way, these high-performance probes should be recreatable by everybody cheaply on a normal FR4 process. There was even a nice and flat metal plate included, courtesy no doubt of PCBWay's mechanical fabrication services. These 2 active voltage probes seem to be part of a larger undertaking by the creator. In the same theme of making more capable tools available to people more freely, he's also launched a software project called ngscopeclient that can absorb raw oscilloscope ADC data and just take over the processing on a computer, ultimately giving older, discontinued, yet capable hardware a new life by unlocking state-of-the-art capabilities, or one-upping stiff manufacturer-supplied software options with the limitless flexibility of open source. Really cool projects by Andrew Sonnenberg, a few linked below. This single-ended active voltage probe called AV1 is based on TI's Buff 802 chip, a $6 3 GHz JFET input buffer. The overall BOM cost for one of these was around 70 to 80 euros, and while we don't get any kind of performance guarantees, like we would with high-end, high-dollar professional equipment, I don't doubt that this will perform nearly on the same level as these guys. Once trimmed correctly, both in terms of high-frequency trim and shortening the leads. The probe can be USB-powered and help us make rise time measurements on nano and maybe even picosecond lasers if I ever find any, with the lowest parasitics for an undisturbed experiment. But we were just talking about differential probes, so let's continue there. Direct oscilloscope channels are unsuitable for mains measurements for exactly the same reason that makes them unsuitable for high-speed differential signals. The B and C connector shells to which they are referenced are mains earth usually, so something bad happens if another mains earth referenced signal is connected to them. And a differential transmission line driver is usually just about strong enough to drive a few meters of cable, not your whole city. For the former case of slow high voltage stuff, there are plenty good options. AKL84 here is mainly for high-speed digital differential signals. And that is a very, very important job, because those are everywhere nowadays. USB, Ethernet, PCI Express, HDMI, DisplayPort, the Centronics parallel port. The reason for this popularity is simply that the difference between two signals remains the same, even under an external EMI influence. Some of these mass-produced consumer technologies, especially the latest, highest throughput versions of PCI Express and HDMI and stuff, rely on such high data rates on multiple lanes simultaneously that many gigahertz technologies are needed to diagnose them. AKL84 here is based on a $50 6.5 GHz differential amplifier IC. With that we can get a first glimpse at such high-speed differential signals. But this kind of thing seems to be outside of the scope of MXO4. Let's say we want a quick, intuitive way to judge the signal quality. The usual tool for that is called eye diagram, and it's created by triggering on bits and overlaying many waveforms with some display persistence. Jitter and noise would cause a thickening of the resulting trace, so the eyes would be closing and that would be an indicator of a poor signal quality. A visual example coming up in 1 second. Now, these technologies usually don't expose a clock for us to conveniently trigger on, so oscilloscopes intended for that job will usually have a feature called clock recovery, where they look at edges and their timings and make a best guess towards the underlying clock frequency. We can trigger on all edges normally, but edge timing is part of what we are trying to analyze. So while looking sexy, this would only give us half of an eye diagram. And anyway, at a mere 1.5 GHz. We are playing several leagues below those really state-of-the-art big data interfaces, so it's not unexpected that we are not fully kitted out for this. What if we really need it though? Or some other obscure processing feature that an oscilloscope manufacturer might have not thought of? Let's see what the aforementioned open source software can do for us in that case. I was able to get MXO4 superficially supported by modifying an existing Rohde & Schwarz RTO6 driver in the project. It's still early days for these scopes, with a lot of work left to do. But a trace on the display is all we really need to put ngscopeclient to work. Clock recovery? Easy, just grab one out of the list of available filters. Put it on a workspace and connect an oscilloscope channel to its input. Boom, it gives us its best estimate of what a common clock for that bit stream might look like. Eye pattern? Not much harder to generate. This one wants our newly derived clock and scope channel data. And there we are, I think. No idea what I'm doing here. But this seems like the best thing that could have ever happened to digital oscilloscopes. And this is only a fraction out of so many capabilities, available soon with so many scopes and other hardware. Next probe, the little B, B1, from B-Field Labs. I've briefly flaunted it in another video. This is an open source hardware DC to 10 MHz magnetic field probe. With only 2.5 milligauss of noise in its most sensitive range, it is able to sense Earth's magnetic field, and assist, no doubt, in many physics shenanigans. Last time I didn't have this yet. This is a slitted ferrite toroidal core in a 3D printed shell for clipping onto little B's stinger. This was hard to make, because FYI, ferrite is very hard. But the reward for success is huge. This flux concentrator turns little B into a DC to 10 MHz capable current probe. Another accessory that top-tier oscilloscope manufacturers would happily charge thousands for. And again, I'm not saying that that isn't justified. If we use it to develop some product that earns us millions, then we just value something that works right out of the box and is guaranteed to operate within some specifications. But for education or just getting a lab started, this is another crazy capable tool to have. And it gets even better, well, depending on whom we are asking. We can boost its low current sensitivity by using a higher permeability core and more windings on that. By sending two currents through opposing windings of exactly 1:1 ratio, we can compare them and find out exactly when they are equal. Sounds lame, but is super valuable for resistance metrology. If that doesn't get you excited, you are probably a restaurant owner who's fed up with fees for credit card reader hand terminals. Well, I've got good news for you. With the little B1 and a Rode & Schwarz MXO4 oscilloscope, you can now make your own. Last probe of the day. I didn't even know these existed until recently. Tastkopfstromschiene, also known as power rail probes. Designing and testing of DC power supplies might be the most common task in all of electronic engineering. Every stupid little thing needs them, and if they are not DC enough, that can cause a lot of time-consuming problems. In many cases, it might be good enough to AC couple a scope probe. In case of MXO4, that would give us a 7 Hz high-pass filter, cutting off all DC content so that we can really zoom in and get a good look at the noise. But what if there's noise hiding below 7 Hz? It's not often a huge problem, but if it is, such low-frequency noise is the most devious type, because it needs large filter components to defeat it. Our scope here has another method built in. Its 12-bit ADC sees 16 times as much detail as conventional 8-bit scopes. In a 1 volt per division range, that could resolve down to 2.44 millivolt steps, simply by zooming in on a 3.3 volt trace, for example. That should be good enough for verifying the supplies in digital designs and consumer slop. For science, instrumentation, metrology and hi-fi, we want the ultimate power rail probing solution with no compromises. This open source hardware power rail probe by blinkenlight.co.uk, or its brand Parradar that also sells them ready-made, is just what we need. It's basically an adjustable low-noise voltage source that can offset away the DC portion of an input signal, leaving only the noise, but with all the scope's bandwidth and vertical resolution still intact. While building my own, I thought I'd skip the $22 power switch in the BOM and substitute some seemingly equivalent harvested part. Just as an FYI, in case any of my fellow cheap fox want to try something similar. The intended part turns out is a left-right switch. If instead you wire in an up-down switch, that will short out the 18650 cells and vaporize a trace. Best case scenario. But with that repaired, we can verify a slightly less than optimal LT3045 ultra-low noise linear regulator implementation. One of the lowest noise, highest power supply ripple rejection parts on the market. Can it reject whatever my cursed mains filter-based DC to DC converter is putting out? The probe helps us find the optimal offset setting with 2 LEDs. I haven't learned my lesson, and so I've also substituted the intended potentiometer with an old precision wire potentiometer. Its wiper skidding over the wire is what's causing the flickering here. A bit annoying, but once we are at 0, that shouldn't matter anymore. The regulator specifies 0.8 microvolt RMS noise between 10 Hz and 100 kHz. When setting the scope to a 100 kHz low pass, we will see DC to 100K. And I think we are well below the specification, so this is all excellent. Very happy to have a power rail probe in my, do I dare say arsenal? Here's how the old 7812 would behave in that same dire situation. Not as good, of course, but hey, this is also less than 1/10 of the LT parts price. And let's not forget, we tested one of its relatives once, for 0.1 to 10 Hz noise, and it was doing superbly. Anyway, that's it for this one. In summary, MXO4, best universal oscilloscope I've ever used. It will probably be improved even further by Rode & Schwarz. And some open source hard and software can really take it to the next level, completing and even adding functionality to its already vast repertoire. Thank you for watching. Please support the amazing open source projects linked below.